A very good morning everyone and welcome to Codenomicon's webinar, Fuzzing 101, Connected Devices, Same Problems, Different Devices. My name is Rikke Kuipers and I'll be your host for today. Today I would like to talk about connected devices, what connected devices actually are and what makes them connected devices, and how connected devices have changed standard network topologies over the years. The next point in the presentation I would like to look at 4 of these connected devices: wireless routers, network printers, network attached storage and internet enabled televisions. We'll talk a little bit about what the vulnerabilities are or the weak points in these devices, and discuss a few vulnerabilities found recently in these devices. In the end I would like to address the problems which are commonly found in these devices, how you can find them yourself and eliminate these vulnerabilities in the devices before you use them yourself or before you deploy your hardware and software if you're a manufacturer or a vendor yourself. And this can be done with fuzzing, and I explain a little bit about what fuzzing exactly is. So to begin with, I would like to take a look at a traditional network, let's say 5, 10, 15 years ago. A typical network would consist out of routers, switches, cables of course, and about a standard desktop PC as we know them and as we see them here on this picture, and maybe servers. Of course, if you think about an office environment, there used to be a printer connected to a computer, which was usually done through USB or to a serial connection, or FireWire for that matter, directly to the PC itself. So there was no way of easily sharing a printer through a network other than setting ports open on the computer itself or through other means on the network. However, this is not the case anymore. Of course, nowadays everyone wants to print from a lot of locations, from wireless devices, and should be available for everyone, and not just if the computer where the printer is connected to is on or has sharing enabled. So of course the solution for this is connecting the printer directly to a router or a switch in the network, and making the software in the printer so that it's open for people, so it's shared. So it gets network capabilities, hardware wise and software wise. For example, printers nowadays are not connected to computers directly, but through Ethernet on a router, or even through wireless to your wireless router. And this change can not only be seen in printers nowadays, but in a lot of other devices. So here, very quickly, on the left side is the traditional network topology from a while ago. On the left side we see the evil internet separated from the internal network through a firewall. A lot of times the firewall is built in, if you think about for example a home office, in a router itself or in a modem. And on the right side we see a desktop PC. Nothing really special. As mentioned earlier, this change, this change of devices becoming connected devices, so getting network awareness and network connectivity, being able to talk to other devices and being able to send data, for example, through the internet or through internal networks, is happening now in many devices. For example, if you take your fridge nowadays, some fridges have the capability of exactly knowing what's inside of the fridge, and if you're out of one specific product, ordering or sending a shopping list to a caterer, which then sends the groceries to your house automatically. So there's not even any human interaction needed anymore. You can think about your oven, which can be remotely controlled using a tablet or your smartphone or your computer. You can think about toothbrush, an electric toothbrush, who sends your brushing habits automatically to your dentist whenever you have a scheduled appointment upcoming. So this whole change of devices becoming connected devices can, of course, has a lot of effect on like traditional network topologies, and which we can see here in the following picture. On the left side we still have the evil internet, possibly or most likely separated by a firewall, at least as far as it goes from the internal network from the internet. But on all these devices aren't static anymore for your network. For example, you think about a photo frame or a laptop or a mobile phone or game consoles. These devices leave your network on a daily basis. They go and enter hostile networks where they're open for attacks, where network policies might not be as strict as in your own home office or in your own office at work, and are open for attacks and are attacked on a daily basis. However, in the evening when you come home, or in the morning when you leave your office, depending on what perspective you're looking at this problem, these devices enter your own network and can thus carry, for example, viruses or whatever type of malware into your network. Whereas then the traditional approach of being firewalled from the internet doesn't really help anymore, because you're being attacked from the inside out. Technologies that help evolve this, Internet of Things as they call it these days, are, for example, IPv6. Every device in your house will eventually get an IP address and will be able to connect out or connect it to from whatever network or internet network on the planet. So it's interesting to look what exactly happened in these devices when they became connected devices. We picked out 4 devices at Codenomicon, we tested these devices, and I would like to share you the results of these and just have a general discussion about what is actually in these devices and what happened over the last year with these devices. If you look, for example, at this picture, which is just a random picture of a router, which you can find nowadays commonly in offices and in people's in consumers' homes. If you think back about the picture where I showed you the traditional network topology, you would see that you had one modem which would, well, let's say like 10, maybe even 5 years ago, typically translate one technology into another. You can think about the translation from DSL or fiber and cable into Ethernet. To which you would then connect all your devices in your router. That was the main functionality. And a lot of times, even further back, you wouldn't even have any routing capabilities in the device. The device itself was just in bridge mode. So, for example, no network address translation, etc. However, nowadays, these devices, as you can see here on the picture, on the left side there's a USB port. And in the middle there are 4 Ethernet ports. And this not to see in this picture, but a lot of devices also have VoIP ports nowadays, which are used to connect voice over IP telephones. So calling over the internet directly using software which is built in or implemented in your router. So this technology, which was like in early days dedicated software on, for example, servers running. If you think about the USB stick, which you can now insert into your router, which can, or USB stick, let's just say an external hard drive, which can contain your pictures, video files, or whatever files you want, and directly share them over the network. This used to be the dedicated function of a server, which had specialized software written for that, with all the security security countermeasures implemented. However, nowadays this is just a little piece of software running on your router. And in the case of VoIP, a full-blown VoIP server used to be a dedicated machine, but is now just integrated in your router in your office. So there are many of these protocols which now run on this device. If you go down the list, it's IPv4, of course, IPv6 nowadays. Or also more common, just the IP stack, HTTP server for checking out and setting your settings on the device itself, so configuring your device. UPnP protocol used mainly, this is DLNA, really popular protocol nowadays to stream, for example, music or movies over the network to your TV, and could also be from your device to your mobile, from your router to your mobile phone or tablet, etc., etc. IPsec, if VPN tunnels are set up to your device. SIP, used for internet telephony. Many file transferring protocols such as FTP, Telnet, NFS, CIFS, etc. to be able to, if you have this network, if you have this hard drive attached to your router, transfer data to it and from it. And coming with the web interface, as mentioned earlier, of course, many web technologies or protocols sort of are used in these web pages. in order to give the user a shiny interface, which is easy to navigate to and easy to change settings, XML, HTML5, etc., etc. Then there's, of course, Bluetooth and wireless in these devices. Since we're not sitting in a lot of cases behind only a desktop PC, which is really static, usually still connected to a cable, but we're also having laptops and tablets and, as mentioned earlier, photo frames or game consoles, printers, which all want to be connected, which you all want to have connected to your network wireless. And many more. Just the possibilities are unlimited. A lot of these devices have, for example, torrent clients, which can automatically download your favorite TV series for you on a given time if you would want it. A quick look at my a screenshot of my web interface of my router, for example, shows already that there are so many options here, which contain so many protocols and which can be configured, that even if you would already configure, even if you would like have protocols implemented which are not vulnerable by default, still you can make a lot of configuration errors because there are so many options to choose from that you can set, for example, ports open to the internet and make your device vulnerable for attacks, even though that's not your intention. So to discuss why this is an interesting device to attack for attackers, there are several reasons. These are just the ones that I found were the most interesting to mention here. Let's say that you find a vulnerability in one of the protocols used in a device, and you want to attack a lot of people at the same time, or a large group at the same time. It's easy to find these people, since ISPs nowadays, they hand out large batches of the same hardware to customers. If you think about a typical ISP in let's say the US might have like 1 million, 2 million customers. They use the same type of modem, the same hardware and the same software, probably for, let's say, half a year, maybe longer, and they send them out to all these customers at the same time. Everyone is running the same software version on the same hardware. So let's say that you find a vulnerability in one of the protocols used or implemented in the software. It would be very easy for you to attack and find people that, or for an attacker, so to say, find vulnerable routers, because you can just go to whatever internet registry is, like have information about the IP addresses used by the ISP and target those IP addresses, just do a large scan on them. Another approach, of course, is also that if you, again, one example here in Finland, we have one provider which has in the wireless network name, the SSID, has the name of the provider in there. So if you would know, like, well, this ISP has from this specific ISP uses these kind of routers and has a vulnerability in let's say their wireless configuration or in the wireless hardware and software, then you can also more like do a more targeted attack on these routers by just scanning the neighborhood or just scanning the area in which you would want to find vulnerable devices. And a problem is why it's such a big problem nowadays is that, first of all, if you already have the knowledge of of how to update software on your device, or that even start like more in the beginning, if you even know how to approach your device, how to find the web interface and how to configure options used in the web interface, and you know, and of course if there is a patch available for your software, you know how to download that and install it, it's still not really pleasant thing to do, because all your settings, think for example about VoIP username and passwords, settings for your sharing of data on the network using whatever sharing protocol you use, settings when it comes down to your wireless encryption, etc. There's a big chance that they will be reset and wiped and you have to enter them again. This is not something that normal consumers or network administrators do or want to do, or are even capable of doing on a monthly basis. As another aspect of why this is interesting to attack, of course, it's a gateway to the rest of your network, meaning that if you own the box, so to say, if you have shell access to the box itself, which has advanced routing capabilities, you can attack attack other devices in the network itself. You can even change the routing so that you would route network traffic to another device that you would own yourself, and for example sniff usernames and passwords and whatever you would want to get from the data itself off the wire. And this all is very hard to detect because it's at the edge of your network. There's no easy way of how to detect that your device has been compromised, solely because people are not skilled enough to well, let's say most of the devices run on Linux, not skilled enough to see whether their Linux box, the router in this case, has been compromised. And B, a lot of times you don't even have this lower layer OS access to the device itself, which makes it even more impossible. And standard software solutions such as virus scanners or IDS, IPSs are almost never implemented on routers. Then there's of course also the some other risk that you have is denial of service, meaning that if there's a vulnerability found in software running on your device, people can crash your system. And of course, if you take the example of the ISP again, you can just do a big sweep, and so have thousands of people calling to the help desk because their device crashed and doesn't boot anymore. Loss of confidential data is what I mentioned earlier already, especially now since hard drives are attached to these routers and there's VoIP capabilities on. It's of course really easy to get your hands on information which goes through your device or is being routed through your device. Installation of malware, sending for example spam from your device, is one thing that's interesting for attackers. Unauthorized configuration, as mentioned earlier, the changing of your routing table in your router itself, so that data is routed differently than to where you actually intended it to route to, and thus gathering information about networks and passwords, etc. This year at DEF CON, hackers published a long list of vulnerabilities found in Huawei routers. These routers are not the big heavy network routers as you would expect in ISP networks, but rather small routers which you can find in offices and just normal consumer usage. These vulnerabilities which were found were heap and stack overflows, and according to the researchers who've done these the research to these vulnerabilities, were very exploitable and easy to write exploits so that you could take full control of these routers. Dan Kaminsky, who found a big DNS bug in 2008 and works at Cisco, said it was a prime example of a platform where you would write easy exploits on. So this just shows that that finding these vulnerabilities in routers is not something that could possibly happen, but is already actively happening at the moment. Another interesting group of devices are network printers. Network printers were among the first group of devices to get advanced network capabilities. This was pushed by the need of the end user. Printing needed to be done at any time from anywhere. An example would be two offices in the same company, geographically separated from each other. There's of course not just the time difference, but there's also the physical distance that makes it hard to share hard copies of documents with each other. Printers with network capability solve this problem. It's of course not possible to print your documents out on any printer connected to the internet, or smaller network for that matter. Printers have evolved from a hardware perspective as well from a software perspective. A standard printer nowadays looks hardware-wise a lot like, let's say, a computer. It has a decent CPU, a hard disk, memory and a network card. But the ways to send a file to the printer is not just limited to an Ethernet cable, but which used to be like that in the past, but for easy transfer from your pictures and documents from a camera or for example a laptop, all sorts of memory readers are now present in the printer itself, like an SD card reader and USB ports. Next to that, of course, Bluetooth interface and wireless interfaces for connectivity with even more devices. Printers are not just limited to printing anymore as well. Many devices have LCD screens on with which you can edit and preview documents and pictures before you print them. This brings us, of course, to the software part, where printers need to be capable of decoding many formats which they get delivered in all these many ways, and process the things that you do with those files on the LCD screen. And this requires not only processing power but also advanced software being integrated in the device. Printers nowadays are multi-purpose devices as well. I mean, with a general printer you can also scan and you can fax, and it's an email client, and it's also a mail server with which you can receive files. And of course all of these ways to transfer files to the printer itself, and all of the ways to send files from the printer itself and edit devices on the printer itself through the LCD screen only broaden the attack surface of the printer in this case, which is already quite large at the moment. So with everything that I just explained, it is of course a really interesting target for attackers, because it features a full operating system, which is interesting later on when an attacker has, for example, permanent access to your device itself, because a lot of libraries that he wants to use are already present, or it's really easy for the attacker to, for example, compile new software on your system, because also of the powerful hardware being present there. It contains a large hard disk. This could be because the reason for the large hard disk, there were two reasons. The first one is people need to be able to send large or transfer large files to the printer, and that's stored on the hard disk, whereas before it was usually stored in the RAM memory of the printer. But if you think, for example, about pictures which need to be edited first, and those edited first need to be stored somewhere, that can cost a lot of memory if you want to do it in RAM, so it's now done on a hard disk. But it's an interesting point for an attacker, because he or she can store information on that hard disk, or for example his own programs, and he can capture also everything that is stored or has been stored on the hard disk, which is usually sensitive information that other people send to the printer. Printers are of course accessible from I wouldn't say all the corners of the internet, but from a network, but from a lot of places in the network, because it's a shared device. So what you will typically see is misconfigurations in, for example, VLANs which are made in network. A printer has access to, or people have from all VLANs access to the printer VLAN, but a printer on its turn has also access from the printer VLAN to all the other VLANs, which is of course bad practice, because if you own then the printer, you can reach the whole network and possibly even go through VPNs if this is set up in the example that I explained in the previous slide, to offices, to geographical locations, etc. What I mentioned already, clear enough now, is easy access to sensitive data. People send documents there, email documents, etc. And as well as many of these printers are now open to the internet, because people want to print these print their documents from anywhere. There's no protection in place, again, against any attacks. People can't access the lower OS layers to detect these kind of attacks, and there is no software in place on these devices that can detect an attack or can detect tampering with the device. Then one other critical point is patching. Patching is not very likely for several reasons. I think the main reason is that a printer needs to be accessible at any time, at any moment. And if you would patch the device, it might be that you lose your settings and you have to put the settings back again. And it's also a device which is which is always in the network, but it's not really like heavily monitored by sysadmins, for example, or whoever owns the printer or owns the network. because it's still just seen as a printer that prints paper with letters on it and doesn't do anything else. This is an interesting article which I found. It shows how severe actually vulnerabilities found in protocols can be. There was some research done by the Columbia University which took one line of HP printers. HP is the world top printer manufacturer in the world now, by the way. What they discovered was that the firmware with which you can update a printer is the firmware was unsigned, meaning that you can just upload whatever software you want yourself to the printer, and then adjust the software. And then of course it's adjusted software, so you can do things with the printer which you normally can't do. For example, what those researchers had done is they had changed certain levels in the firmware which were sending commands to the fuser, which is used to heat the toner of the device. So the heating would go like to a really hot level where the paper even started to get brown and started to burn. Of course, this is not something that you would like to happen in your own office or even in your own home, that your printer starts burning all of a sudden. And one of the reasons why this is a really like real life scenario is that a lot of these printers, the web interface, where you can change these settings of the printer but also upload new firmware, is usually open. There's still the default password set to access these pages, which is admin, for example, username password, which makes it an even more also life-threatening vulnerability. The next device group I'd like to talk about are network attached storage devices, or NAS devices in short. Network attached storage devices are essentially specialized computers which operate as file servers. This means that they have built-in operating system, such as Linux very often. Choice of Linux is because of the modularity of Linux itself and the relatively small size of the OS. In addition to that, usually also a really low memory footprint when running applications on Linux-based operating systems. The file sharing protocols implemented in these devices are usually in the lines of, for example, CIFS, HTTP, SFTP and FTP, NFS, Samba, etc., etc. And these devices have become way more interesting for companies because they're very affordable. They are widely available as well. It's an easy switch to go from large, expensive, time-consuming for maintenance server parks for storage to go to relatively small network attached storage installations, which in this picture is really small, but you can have them in a slightly larger version with a little bit more storage in them, which is easier to maintain and doesn't require a network engineer monitoring and maintaining the system full time. Apart from that, there is of course the trend that we see is that there's an ever increased need for storage, for storing more data. If you think, for example, about picture size, to take a really simple example, picture size not that long ago was maybe let's say half megabyte, and nowadays it can easily be 30 megabyte already. Same for movies. A movie used to be 800 MB from a CD, and nowadays if you take a Blu-ray movie it can be easily 30 or 40 gigabytes. And then of course we're talking here about consumer usage, because on these devices nowadays the software which is still not available consists out of torrent clients or news leechers, which enable the consumer to automatically pull movies or series or whatever else type of data from the internet, and then also stream this. So there's also stream protocols such as various types of UPnP implementations in these devices, which enables the user of this device to stream the movie directly to the TV or to a tablet, etc. If we look at the rest of the list of protocols in this device, it's kind of like the same as with the router and with the printer. file sharing protocols, protocols that are used when configuring the device, for example HTTP to the web interface, and in the web browser there are of course many web technologies used, etc, etc. And then we have the standard IP stack and all the other, so to say, standard network protocols. So once again, this is an interesting target because it contains even more than a printer. Sensitive data from users. Users upload, if you think about a small company or even a large company, upload all their projects, if you think about a software company, to the network attached storage device. All their documents, HR might store their payroll information on the device, etc. Next to that, of course, detection is again really hard because you don't have access to lower layer OS functionality. There's no built-in virus scanners, etc, etc. Added to that, there's so much traffic going from and going towards the device that it's really hard to filter out what is exactly going on the wire. And it's again hard to patch because you don't want any downtime for your storage facilities, because that means that you might have to store your data somewhere else, if you, depending of course on the setup of your devices. It might also be that you want to have the patch level the same over all your devices. If you have several of these systems, you need to take everything down at the same time, which is not something that you typically would want in a production environment. Then there's also an even bigger threat than denial of service vulnerabilities for printers, which can be critical, but is not really, it doesn't have a high impact. But if you think about storage, if your employees are in need of the data that is stored in these devices, if you have a device that crashes, then the downtime can be really costly for a company. And the last point on the list is the same as for the other devices. It's again a device which is in the center of your network and which can most likely reach all the VLANs or reach all the subnets in your network, because most VLANs also want to have access to the VLAN where this device itself is. Recent vulnerabilities are in the EMC Celera network attached storage. It would accept external network traffic. It was because these devices are, of course, but I've failed to mention, connected to the internet directly for people who want to access their files also from home. If you think about the example of an office network which has storage, central storage. So it was possible in this device to access IP addresses which were internally in the network from the outside, and it was also possible to use NFS requests to read, create and modify files which were stored on this NAS device. This has been reported and this bug has been patched ever since. This is just one of the examples that I found on the internet. There are like hundreds of these vulnerabilities actively exploited and abused by attackers. The last group of connected devices I like to talk about are internet-enabled televisions. This might not be the first group where you think about connected devices, but this is, in my opinion, a group of devices which is going to be really important in the future in terms of vulnerabilities being found in these devices and actively exploited. Not so long ago, a TV was just a device where you would watch, of course, television on, but nowadays these televisions have, the same as the printers and the routers and the network attached storage, advanced hardware inside of a TV. And the software that's running on these TVs in particular is really similar as the software which is running on tablets and sometimes even laptops, depending on the brand of TV that you have. It's possible to check your email on these devices. It's possible to Skype with friends or family. It's possible to access various online services such as on-demand DVD and video and series and music watching and viewing. Hardware-wise, these devices have a wireless interface, a Bluetooth interface. They have, of course, a plethora of network protocols built in by default, but also many other protocols which you would typically find on computers, because they have full-blown browser built in, with which you can basically do almost the same as you would on a desktop PC or a laptop. Then they also have, same as a printer, USB slots and SD card readers, and they have decoders for images, for audios, for videos, for many file formats as well. You can read PDFs, for example, on them, and so on and so on. Besides the whole aspect of vulnerabilities being present in software and the protocols on these devices, it's also a whole different view from a social perspective, since normally you would trust, I would say, almost anyone with access to your TV, but you wouldn't trust anyone with access to your laptop, because there's a lot of personal information on your laptop. But these TVs have the same capabilities as your laptop has, because there's also your email access, there's also your files on there which you might not want to share with anyone. There's also your Skype account, there's also your chat client, etc., etc. However, a TV is always within reach of everyone entering your house, or even entering, for example, your office. And it's not uncommon for people to interact with your TV on a free basis, which is differently in comparison to, for example, your laptop or your desktop PC. I'd like to take this moment to mention that we have, for each of the devices which we discussed before the TV, and also for the TV itself, a white paper online which goes more technically in depth on the vulnerabilities we found ourselves in these devices and which typically exist in these devices. In, for example, our TV white paper, we have a little discussion about DVB fuzzing, which is quite an interesting attack vector to TVs, since even if a TV is separated from the internet itself, an attacker could still attack the TV using the DVB streams or the MPEG transport streams, which is inside the DVB signal. So just to be clear, DVB signal is the signal which you normally would receive through the wire, for example, your DVB cable. DVB-C is the protocol used there, or through your antenna on the roof of your house, DVB-T, T standing for terrestrial. So one thing that we've done is first these DVB streams going to the television and monitoring the television to see when it crashed or not, and so finding vulnerabilities in the DVB N and decoding of the TV itself. This is quite an interesting aspect, because that possible attack vectors could be that you would stand outside a house with a really big antenna and override the signal in someone's home, and thus effectively like exploiting a vulnerability which is present in the TV itself. So once again, more in-depth technical discussion about this in each of the white papers for these devices. Televisions are quite interesting targets for attackers, because their attack surface is really broad, and I mean by this that there's a lot of ways to attack your TV. There's almost everything what you can find nowadays in laptops and in desktop PCs. Apart from the fact that the biggest difference is here that in standard computer devices such as laptops and desktop PCs, there is antivirus software available. There are standard countermeasures available against these kind of attacks, which aren't available for TVs. Again, you don't have access yourself to lower layer OS functionality, and these TVs are also quite similar in terms of hardware when it comes down to, when compared to laptops, for example. They have quite good CPUs nowadays, because they need to do the decoding of various protocol of various file formats, if you think about the images and the video and the audio. It's also a very unexpected attack vector. No one expects that your TV is being compromised or has been compromised, and that your other devices in your network are being attacked through your TV. And of course, attackers take advantage of this fact. Then there's also the point where the life cycle of the TV is generally short. I would say that a manufacturer expects that the TV is nowadays 2 to 5 years being used by a consumer and then thrown away and swapped by a new TV. So there's only support in the term of security patches for 2 to 5 years, which is quite a small period, I'd say, especially if you buy a little bit older TV. There might not be that long support still on the software on the TV, which makes it a vulnerable target if security holes are not being patched. So how can you find these vulnerabilities in your software? Well, I would say the main way to find these vulnerabilities is through the use of fuzzing. What fuzzing is it's the sending of unexpected inputs, are called fuzzers, so random data, to the device which you're testing, the SUT, system under test. In this picture there's a quick example of a device being fuzzed. At the left side there's the laptop running the Fuzzing, on the right side there's the device being fuzzed. We see here the use of the HTTP protocol, which is used in, for example, getting the index page of a website. So what you could see is similar as the left side is using a browser, the right side is a web server. In the first request we see that the laptop is requesting the index page of the device. We see that the laptop does a get and then a slash and HTTP 1.1 and some other information sends in the packet to the web server. The get slash means that it wants to get the first page of the web root of the web server. The web server gets the request and sends an HTTP 1.1 200 OK back. This 200, this HTTP code says that you send me a valid request and I accepted it, and here is some, you see here the header information of course, but beneath that in the same packets and the packets that are following is the web page itself, which is then received and displayed by a browser. In the second request we see the first anomalous request. We, instead of the slash, we input a lot of A's there and then send it to the server. In this case the server sends an error code 404, meaning that the resource is not found on the server, and sends that back. This is standard error code. This is expected behavior also, because the resource doesn't exist on the target. In the next example we see that we send a lot of random or more random characters to the device itself, and the device, the software running on the device, doesn't know what to do with that, because it for example generates a crash in the logic because it sees their characters. In this case it's the percent sign, which it doesn't which it can't process, and it's generating an error code 500 internal server or error and sends that back. You can also see here that there's some other anomalies in the response back. We see the content length is -1, the content type is some weird characters, etc. Then in the last request, the resource that we're asking from the server is even more anomalized, and we see that the server implementation can't handle the request it gets and crashes totally. And in this case, a crash, you can safely assume that you found a crash, meaning a vulnerability, and it could be or could not be that this vulnerability could be exploited, and attackers could take advantage of it and write, for example, code for it that will execute once this anomaly is triggered. So really quickly, not to go too technical, on the left side you see the anomalies which we can send to the device under testing, and on the right side we see the vulnerabilities. I won't go into any of the anomalies now. You can download our more technical Fuzzing white papers from the website, but on the right side I want to look quickly at that. So we just saw that the server crashed, but that's not the only thing that you can see or can trigger by fuzzing protocols in your device. You can, for example, have denial of service. Denial of service events, meaning that the device just doesn't reply anymore, or can't reply to other requests from other users of that specific protocol because it's too busy with the request you send to the device. You can have security exposures. One example of this is that when a crash occurs in the device, it just drops the content of the memory of the device on the wire, which is of course not good because there could be sensitive data in everything that's stored in the memory of the device. Performance degradation, meaning that the request you're sending there, the CPU is so busy or occupied with trying to go through those requests that that all the other services that the device is performing are really slow or even on hold. And that's in the next point. Then there's thrashing, and then there's anomalous behavior, etc., etc. There's almost an unlimited list of things you can find in your device while fuzzing it. Of course, all of these things are vulnerabilities. So why should you fuzz? Well, first of all, you can eliminate all these vulnerabilities or find these vulnerabilities in your software yourself and patch them before you roll out your software, or before you roll out your hardware containing software. Secondly, of course, it's also a money issue, because what you want for your developers is to focus on what you've hired them, which is developing new functionality for the product that you're rolling out. In the case that there's a vulnerability for your found in the software of your device and your product is already out there, then your developers have to patch the vulnerability, roll patches out. In the case that there's an exploit for a vulnerability found in your software, then your developers need to reverse engineer this exploit, then patch the vulnerabilities, and then roll out the patches. This is of course a really time-consuming thing, which is not what you want for your developers, because that's not what you hired them for. Apart from the aspect of money, there's also the aspect of your customers, of course. If you have a lot of vulnerabilities, a lot of bugs in your software, if your customers are getting hacked, they will be angry, and they won't buy your product anymore. They will call to your call center, complain about their servers are being down again, or they've lost some confidential data because there were bugs found in the software, etc., etc. So there are many reasons for why you should fuzz. To eliminate, but I would say the main reason is to eliminate bugs from your software in order to stay safe for people who have less good intentions when searching for these bugs in your software. One other thing is, of course, that we've only been talking now from a perspective of an attacker, and so only been talking about an attacker attacking your software. But there could also be the case where your software just has a vulnerability or a bug. Also, you can also call vulnerability a bug in the software, and crashes and sends random data on the wire, and other devices on your network receive that data and crash themselves. So if you already have fuzzed your device, you can find these bugs in your software and make sure that even if there's some garbage data on the wire which is received by your software or by the protocols implemented in your software, that they don't behave in a way that you don't want them to behave. So this is a quick slide about some results that we found while doing fuzzing in the connected devices we talked about. So network attached storage table on the left, you see that there's for each device in this category, these are 5 devices from a different brand. So for each device there are protocols on which they fail, although some of them might pass a specific protocol. For example, in this case ICMP for IPv4. What this means, of course, is that hackers or attackers will always go for the low-hanging fruit. So they will just keep on fuzzing all the protocols which are implemented in your software until they found a vulnerability. So even though one protocol might be saved, then they just go on to the next protocol. On the right side, the same thing for printers. As you can see, there's a lot of red in there. It doesn't look that good. Once again, these white papers can be downloaded from our website to take a more in-depth look into these results. Then I would now like to show you a quick demo of a television crashing. What I would like to demonstrate here is a crash that I found while fuzzing TVs. What I did in order to find this vulnerability was to create an X amount of pictures which were fuzzed. I generate this picture using the Defensive JPEG suite, which per default generates 500,000 images, but of course for this purposes I only put I think around 500 pictures on a USB stick, and I just played them on the TV, just looping through them. So you can see that the first image here it says nicely Codenomicon JPEG test suite, and it's also a picture which is not fuzzed. Then we see images like this where the colors are totally different from the original. This because the codec has trouble translating the images to a nice image on the screen. And what you also see in between is that it says not supported file format. It could be that the file is so heavily fuzzed that the TV codec recognizes that it's not a valid image file and doesn't want to play it. So what you see here is that the TV crashed and is rebooting itself at the moment. So what you see now is that the TV reboots itself because it can't control the crash, but if an attacker were to exploit these vulnerabilities or this particular vulnerability in the picture, he would of course create a controlled crash, so to say, where your TV wouldn't reboot but you would just skip to the next picture, and in the meantime some, let's say, malware could have been installed on your TV without you knowing it. And that concludes my presentation. Thanks a lot for watching and listening to me. I hope you enjoyed it. So I see there are a few questions in the chat box. I will read them out loud and try to answer them as best as possible. The first question: what kind of denial of service bugs can you find? That's a really broad question, let's say. Of course it depends on what you exactly mean by denial of service bugs. I would say that it's pretty wide. You can, for example, have a device which crashes and which doesn't react anymore to any network traffic being sent to the device. It sometimes happens that the device which you are fuzzing stays alive, so there's still communication possible, but other protocols in the device itself crash and don't react anymore to anything. So that's one possible angle to a denial of service vulnerability. It could also be that if you send a certain anomalized packet to a device, the device just crashes and needs a power cycle in order to reboot. So that's the heavier categories of denial of service bugs. So it's quite broad. You can expect anything almost to happen. Second question: how should a corporation mitigate, for example, printer vulnerability problems? Well, if we're talking specifically about vulnerability problems in printers, I would say that the administrator of the printer itself should have the configurations of the printer back up somewhere. He should have a standby printer ready, which he can then load the default config in after he updated the device, of course, if there's a patch available. And if in the case that there's no patch available for the vulnerability being made public in the device, then I would suggest, if it's really critical, to use the device, which in the case of a printer is questionable, of course. But one possible option would then be to isolate network-wise the printer. So put it in a heavily secured firewalled subnet, so to say. So yeah, you really know what data is going to the printer and what data is coming from the printer, or network traffic, sorry. and try to take a look at the vulnerability yourself and try to write based on that for IDS or IPS signatures. So if you see some traffic which tries to exploit the vulnerability, you can catch that and stop it before it actually happens. Another question: are there robustness standards in use that could be required from the vendors? Well, yes, what we see more and more happening is that large organizations push fuzzing requirements to their software and equipment vendors in order to prevent themselves having to do all the fuzzing. One good example would, for example, be Verizon, who makes it obligatory now, or has specified in their Verizon lab entry criteria in the part of the security test requirements that all their vendors and software and equipment vendors should have done Codenomicon fuzzing before they accept the device to be sold to their customers again. There's, if you're interested, a video on our website at the moment from Harry Chu. He's from Verizon, and he spoke at Codenomicon, the conference of Codenomicon itself, last year, 2011, if I remember correctly, and he explains how this was done and why this was done. So I would suggest that you take a look at the website if you want to know more about this. Another question: does any printer manufacturer advertise their security to be good? Well, then I should try to stay objective. In my personal opinion, I haven't seen any, but it goes for all the newer connected devices. I haven't seen, apart from tablets, I have to say, there's some more focus on security when it comes down to tablets. But I haven't seen, in the case of printers, any commercials, at least, which state that the security in their printers is good, or that there has been some testing done. I think all the commercials we see on TV and on the internet and in newspapers are only focused on promoting features being present in the printers, and not per se advertising security being present in the device itself, which of course is a sad thing. It's a sad thing. It should be equally of both, in my opinion, especially if you look at the state of security nowadays of these devices that, well, as you saw in the result table of the Codenomicon tests, all the printers fail on many protocols. That's just really worrying. Okay, I think there are no more questions. If you have any questions later, please feel free to email me at rikke.kuipers@codenomicon.com or support@codenomicon.com. Visit our website and download any of the white papers as well. And then I would like to conclude my presentation, and thanks again for watching and have a nice day.